Welcome to next lecture of Digital Electronics lecture series. So here we are going to explore the XOR and XNOR gates and their applications. So earlier we have seen there are different logic gates, and out of these OR, AND, NOT, NOR and NAND gates, these we have already discussed in our previous lecture. So here we are going to concentrate on XOR and XNOR gate. So XOR gate, the full form of XOR gate is exclusive OR gate, and the symbol for XOR gate is given like this. So here it is not exactly a basic gate. We have three basic gates only, AND, OR, NOT, but combining those AND, OR and NOT gate together, a frequently used operation has been given a form of a gate, so that we are calling as XOR gate, and it is having extensive use in digital electronics, communication engineering, even in today's big data also it is having huge application. So what XOR operation is, for two inputs A and B, output is of the form of A B bar plus A bar B. So this is a typical form of output. So if we elaborate this XOR gate, we find that we have one NOT gate, we have AND gate, and we have OR gate also. So here, say this is AND gate 1, this is AND gate 2. So here we are giving input as A bar B. So here output we are getting A bar B. Similarly here we are getting A B bar. So then we are ORing them, and what we are getting is A bar B plus A B bar. So this thing we are getting as the output. So how the truth table will look like? So here for 0 0 we get output as 0, 0 1 output as 1, 1 0 output as 1, and 1 1 output as 0. Now why this output we are getting? Suppose A value is 0, so B value we have taken 0 0, so B value is also 0. So complement of B, that is complement of 0, we are getting it 1, so 0.1. So this portion we are getting as 0. Similarly here A bar means 1 and B is 0. So once again 0.1 we are getting 0. So output is 0. Similarly, if we have, say, A equal to 0 and B equal to 1. So A is 0, B equal to 1, complement of that we will get it as 0. So we are getting it 0.0. Now here what we are getting, A equal to 0, this one A equal to 0, and A bar we are getting as 1 and B equal to 1. So here once again we are getting 1. So 1.1 is equal to 1. So now when we are ORing it, we are ORing 0 1. So 0 or 1. So we are getting it as 1. So that is how we are getting output as 1. Now what is the uniqueness of this gate? This gate output is 0 when both the inputs are same, and output is 1 when both the inputs are not same. So if any of the input is different, then we will get output as 1, and if we have both the inputs same, then output is 0. So this is the uniqueness of XOR gate, and this property is utilized in many of the electronic circuits. Now XOR gate, it is having some algebraic property. A exclusive or 0, that will give us A exclusive or 1 will give us A bar, A XOR A, that will give us 0, and A XOR A bar will give us 1. So these are some properties of XOR gate, and these properties further extended to this to another property. These are known as De Morgan's theorem. So this De Morgan's theorem is very important in logic gate based analysis or logic function simplification, their De Morgan theorem is having a huge utilization. So what De Morgan's theorem says is A or B bar. So that we are getting A bar dot B bar, and AB bar, for that we are getting A bar plus B bar. So very important property in logic simplification. XNOR gate is just the extension of XOR gate. So here what we are having, a NOT operation after XOR gate. That means it is the complement of XOR gate. So what we are getting here is A exclusive or B bar, and output of this we are getting as, for same output, same input, output is 1. So if we have here same input, output is 1. In previous case we have seen output will be 0 for if all the inputs are same, and output was 1 for XOR gate when both any of the input is different. For XNOR gate it will just be the complement. So if any of the input is different, output will become 0. So these properties are also utilized extensively. Now let us see by simplifying what we are getting as A exclusive or B bar. So Y is given as A XOR B whole bar. So that means if we elaborate this, we can replace it here. So we are getting A B bar plus A bar B whole bar. Now if we apply De Morgan's theorem, if we consider this as our A and this as our B, so De Morgan theorem says that A B bar whole bar dot A bar B whole bar. So now further what we have seen, AB bar, that means A bar plus B bar. Now here B bar is already B bar, so we are getting it as B double bar. Okay, so similarly we can further decompose the next term, that is A bar B. So applying the same concept here, A bar, already we have A bar, so we'll be getting here as A double bar plus B bar. Now what is this concept of double bar? Suppose A value is say 0, then A bar value will get as complement of 0, that is 1. Now once again if I complement A bar, that means the complement of 1, that will give me 0 once again. So effectively A double bar becomes A. Similarly B double bar is B. So this particular expression we can write as A bar plus B into A plus B bar. So now if we multiply these two, so expanding this, we are getting A bar plus AB plus A bar B bar plus B bar. So again, what is this A bar? Suppose if A equal to 0, then A bar equal to 1. So effectively we are getting it as A bar, that is equal to 0.1. So that will give me 0. So A bar or B bar, both will give us 0. So effectively for XNOR operation, the output we are getting is AB plus A bar B bar. So this is an important relation. The output of XNOR gate is AB plus A bar B bar, whereas for XOR gate we have A bar B plus AB bar. So now the application, if we look into XOR and XNOR gate, it is enormous. So they are versatile building blocks in digital circuits, and they play a very vital role in various electronic systems and computational tasks. And they are widely used in various applications, which includes the computer arithmetic, data encoding, error detection, Boolean logic operations. So Boolean logic function simplification, like other basic gates, XOR and XNOR gates, they are also used for the Boolean simplification, logic function simplification and the implementation. Then XOR gate is one of the main digital component for binary addition and subtraction. Then XOR gate, or also XNOR gate you can say. So we have discussed about the unique property. When both the inputs are same, then we'll be getting output as 1, and if any of the input is 0, then output will become 0. So that property of XOR gate is used as comparator. So comparator, there we can use use this XOR gate to compare the different inputs. Similarly, XOR gates are used for parity generator and parity checkers. So for error detection, which is a major requirement in communication systems, so parity generator, checker, for that purpose, yes, XOR gates are used whenever in digital communication we send any information signal which are in terms of zeros and ones. So error correction coding plays a very important role, and their XOR gate is the must requirement. Then for data encryption, so today's world is data driven world, in the world of IoT, Internet of Things, and there we need the secure communication. So for secure communication, for data encryption purpose, XOR operation is used. And a very popular one, arithmetic logic unit. So this is the main component of CPU, central processing unit of whether it is a computer or mobile or any digital device, whatever processor we are using. Inside the processor we have the arithmetic logic unit, and their XOR and XNOR gate we use for performing this arithmetic and logical operations. So bitwise XOR, bitwise inversion, carry generation. So all these operations are done using XOR and XNOR gate. So here we end today's discussion. Thank you very much.